Here is a video on formal game theory notation. This may be the most boring video yet, but it is a necessity. If you open a textbook on game theory, you will encounter matrices and game trees like the ones we have used. However, you will likely also encounter a formal notation of games that can be intimidating and confusing. Game theory uses set theory notation that is very general and allows precise description of every conceivable game, but can sometimes seem unnecessarily complicated or alternatively trivial for simple two-player games. So in order to ease the difficulties of you picking up a textbook on game theory and studying on your own, here's a bit of an overview to familiarize you with the notation. Let's look at a normal form game. A normal form game is defined by the players in the game, the strategies available to these players, and the payoffs received by each player for each combination of strategies. The players are numbered from 1 to n. Now in all the normal form games that we have discussed so far, there were only 2 players, which is why we were able to express the game in form of a matrix, but in principle a normal form game can have any number of players. This is why the number of players can go up to n and not just to 2. An arbitrary player is called player I. Why not player 1, 2 or 3? Because by calling a player I, we can make general statements that apply to a certain number of players. For example, all players or all even players or something like that. Here in the example on the right, we have only 2 players, 1 and 2. Additionally, we need the set of strategies that is available to each player. So capital SI denotes the set of strategies available to player I. SI is therefore called player I's strategy space. Here in the example on the right, S1, the strategy space of player 1, is left and right in capital letters, and the strategy space for player 2 is left and right in small letters. To denote an arbitrary member, so a non-specific member from the strategy space SI, we write small si, with small si being an element of capital SI. So in the example on the right here, small s1 could be left or right in capital letters, and small s2 could be left and right in small letters. By writing specific strategies in brackets, we denote a combination of strategies, one for each player. So here, for example, left in capital letters and left in small letters is one possible combination of strategies. Furthermore, UI denotes player I's payoff function that assigns a payoff to player I for every possible strategy combination, Si to Sn. So in a game where you have 2 players and each player has 2 strategies, in total we have 4 combinations. In a game where we have 3 players and every player has 3 strategies, we would have 3 to the power of 3, 27 combinations. So a payoff function of a player takes a strategy combination and assigns a payoff. So here, for example, the payoff function of player 1 for left-right is 3, and the payoff function of player 2 for right-left is 1. You can check the game on the right to confirm. So now we have everything we need to define a normal form game formally. So a normal form game with n players is therefore defined as G is the set containing all the strategy spaces of the players and the payoff functions of the players. So if we now want to formally define the game on the right, how would that look like? Think about it for a second and formulate the answer in your head. So the definition of the game on the right is this. We have the strategy space for player 1, left and right in capital letters, the strategy space for player 2, left and right in small letters, and we have 2 payoff functions, u1 and u2, that assigns a payoff to player 1 and 2 respectively for each possible strategy combination. So you can see why we usually use matrices to define games and not the formal definition. Well, if you think this was complicated, wait until you've seen the definition of a strictly dominated strategy. Recall that a strictly dominated strategy is a strategy that for any given strategy combination chosen by the other players gives a strictly lower payoff than another strategy. So this here is the formal definition of a strictly dominated strategy. In the normal form game, G equals strategy space of players 1 to n and payoff function from players 1 to n, let Si prime and Si double prime be the feasible strategies for player I. Strategy Si prime is strictly dominated by strategy Si double prime if Ui of S1 to Si minus 1, Si prime, Si plus 1 to Sn is smaller than Ui of S1 to Si minus 1, Si double prime, Si plus 1 to Sn for all S1 to Sn excluding Si. That can be constructed using capital S1 to capital Sn, excluding capital Si. Alright, I can't even read that properly. So let's break it down a bit. So Si prime is the strategy that is dominated, and Si double prime is the strategy that dominates Si prime. Small s1 to small sn are the strategies chosen by all the other players. Note here that in the middle we exclude Si because we are talking about this player I, so the other players are every other player but not I. And capital S1 to capital Sn are the strategies available to all the other players. So with that in mind, it says that for all the possible strategies the other players could play, the payoff of playing Si prime for player I is always smaller than the payoff of Si double prime, which is exactly what being dominated means. Alright, let's see if you're getting used to it. So here's the definition, and you have to guess what the definition is for. So in the normal form game G, which includes the strategy space from players 1 to n and the payoff functions from player 1 to n, the strategies S1 star to Sn star are something if for each player I it is true that the payoff for player I when the strategies are S1 star to Sn star is greater or equal to the payoff for player I if all the other players play S1 star to Sn star, but player I plays Si instead of Si star for all Si's element capital Si. Alright, so what is this? This is of course the definition of a Nash equilibrium. So what does everything mean here? So all the S stars, they are the strategies of the Nash equilibrium, so all the strategies that each player plays in the Nash equilibrium. Si star is the equilibrium strategy of player I, and since it is the strategy in the Nash equilibrium, it must be the best response to all the other strategies, which means that it must bring the highest payoff given what all the other players are playing. And Si without the star are all the other available strategies for player I that do not bring a better outcome than Si star, which is why Si star is the strategy in the Nash equilibrium for player 1. Alright, I'm sure that's quite complicated, however we have good news. So consider an extensive form game, like the one on the right. Now extensive form games are defined by, again, the players in the game, when each player has to move, what each player can do at each move, what each player knows at each move, and the payoff received by each player for each possible combination of moves. Now you can imagine if you write that down in set notation, this gets super complicated, but fortunately extensive form games are typically described with trees and not with formal definitions. So even if you take a textbook, it's quite unlikely that you see a formal definition there. Because for everything but the most simple game it tends to get extremely convoluted. But even if there is a bit of formal notation, now you at least have some idea what it's supposed to mean and you can start to figure out the details on your own.